Welcome everyone. You are joining us for Let's Talk About Metalenses. This webinar is presented by LightTrans International and hosted by Photonics Media. Today you're going to hear from Professor Frank Wyrowski. He established LightTrans International in 1999 and then founded Wyrowski Photonics in 2014. He is also Professor of Technical Physics at the University of Jena. In this session, he is going to share strategies for the design and simulation of metalenses in common application context. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access a recording of this online after the presentation, and you will receive a link to that recording by email. So with nothing further from me, I'd like to welcome Frank Wyrowski. Welcome.
Yeah, thank you, Joanna. And I'd like to add that also Christian, he's also here today. He is co-author of this, and we worked on this talk together. Now comes the most critical part of any webinar, the transition to the presentation itself. I changed to my good microphone and switch off the camera, and then we can start. In this webinar, we like to talk about metalenses, a subject that has attracted significant interest lately. Metalenses represent an additional type within the flat lens category, which also includes diffractive and Fresnel lenses. At LightTrans International, we create the VirtualLab Fusion optics software and distribute it globally through our network of distributors. VirtualLab Fusion is a multi-scale simulation platform that serves a broad spectrum of applications. In this webinar, I will showcase the features of VirtualLab Fusion related to flat lenses, which we plan to release this year. We aim to address various tasks and challenges faced in software development when integrating flat lenses into lens system design and modeling. This inevitably brings us to some mathematical analysis and equations which are essential for a serious discussion. I will strive to keep these concise during the webinar. The mathematical methods are embedded within VirtualLab Fusion, enabling our smart algorithms to perform tasks autonomously. Thus, users are not required to have a deep understanding of the fundamental physics. Nonetheless, we believe its advantages for our customers to gain an understanding of the foundational concepts in our simulation and design. In addition to exploring theoretical aspects, I'll present numerous example simulations during the webinar. To conclude my introductory remarks, I would like to stress that at LightTrans International, we maintain an unbiased stance regarding the significance of flat lenses. Our mission is to equip you with robust software tools that enable you to investigate the significance and use of flat lens technology in your work. Metasurfaces employ nanostructures with a high refractive index, commonly known as meta-atoms or meta-cells, arranged on a substrate that has a lower refractive index. This approach has been recognized for a while, but it has recently gained renewed interest. For an initial insightful read, consult the review authored by Lalane and Chavel. In addition, the informative tutorial by Yang Fan and colleagues is recommended, which includes numerous additional references. Given that metasurfaces are composed of nanostructures, it is clear that the general optics approach is unsuitable. Instead, it is necessary to utilize electromagnetic field theory based on Maxwell's equation, commonly known as physical optics. Thus, incorporating metalenses or other flat lenses into a lens system together with conventional lens surfaces and other components creates a multi-scale system. This requires an approach to optical modeling that spans multiple scales, often referred to as multi-scale simulation. To put it plainly and emphatically, Achieving multi-scale simulation is not possible by linking various optic software tools to data interfaces. Rather, a comprehensive strategy is required, grounded in a sophisticated formulation of the physical optics foundation for optics software. Modeling optical systems across different scales requires the integration of diverse simulation models within a unified physical optics framework. This is the approach that we take with our VirtualLab Fusion software. Among various other technological innovations in VirtualLab Fusion, the advancement of geometric optics for electromagnetic fields enables its smooth incorporation with other physical optics simulation techniques. To achieve this, we adhered to guidance provided several decades ago by the renowned Max Born and Emil Wolf. They strongly advised expanding the foundations of geometric optics to include electromagnetic fields. By employing our unified approach for multi-scale simulation, we can seamlessly link the geometric optics modeling of a traditional lens surface with a sophisticated simulation model for a metalens. This leads to unparalleled speed in multi-scale simulation when utilizing VirtualLab Fusion. I would like to demonstrate the capability of VirtualLab Fusion using this example, where a wafer inspection system needs to be simulated. Simulation models for lenses and the grating are connected in a non-sequential multi-scale simulation. Although this simulation is entirely based on physical optics framework, it conveniently provides access to ray data, which are depicted here. Ray data can be derived from the subset of geometric optics for electromagnetic fields within the physical optics framework. In the focal region, the light strikes the wafer structure, and the reflected light travels back through the lens system to form the image. The outcome is illustrated for the wafer positioned precisely in the focal plane, and also here when the wafer is slightly displaced from the focus. The simulation time for this kind of scenarios is a few seconds on a standard laptop. As demonstrated by this example, VirtualLab Fusion enables fast modeling of multi-scale systems by connecting different simulation models. The primary challenge in integrating metalenses into the multi-scale modeling framework of VirtualLab Fusion is creating a metalens simulation model that can seamlessly interact with the simulation models of other components, such as traditional lenses. Before we delve into our solution for this challenge, let's first address the question, what are the expected results of integrating flat lenses into optical design? To address this question, I would like to present some basic observations. To generate the image of an object point, such as the axial object point, we use a suitable surface. This is the particular surface here for the parameters provided in this example. Replacing this surface with a flat lens does not alter the distances to the object and image planes, and hence it does not reduce the system's length. Next, we add another object point, which requires a distinct surface for accurate imaging. A single surface cannot accurately image multiple object points. Therefore, adding more surfaces to correct aberrations is crucial, a concept well recognized in lens design. There is no evidence to suggest that flat lenses eliminate this requirement. To gain further insight, Let's consider the design of a beam expander. In this case, an initial lens is necessary to transform the incoming planar phase into either a converging or diverging spherical phase. The divergent case is demonstrated here. A second lens is utilized to collimate the incoming light. Thus, the use of two lenses is necessary. The degree of beam expansion is governed by the distance between the lenses and their numerical apertures. Flattening the lenses does not change that outcome. Based on these observations and additional factors, we arrive at the following conclusions. Flat lenses reduce both the thickness and weight of the lenses. The thin design of flat lenses allows for more possibilities in reducing the distance between lens surfaces. The thickness of conventional lens surfaces limits how close they can be placed to each other. This restriction is removed when using flat lenses. The fabrication methods for flat lenses vary from those for traditional lenses, which may offer benefits in specific scenarios. Flat lenses could provide new opportunities for switchable lenses. Interesting research is going on in this field. Replacing thick lens surfaces with flat surfaces changes the aberration dynamics in the system, which may enhance aberration correction possibilities based on the particular scenario. Employing diffractive lenses which exhibit strong and opposing chromatic aberrations to counteract the chromatic aberration of smooth lens surfaces serves as a well-documented instance of this potential. Some characteristics of flat lenses, such as its polarization-sensitive function, may be considered beneficial or detrimental, depending on their use. Later in this webinar, we will showcase an example demonstrating the application of polarization sensitivity. Considering our previous observations, there is no indication that flat lenses, including metalenses, decrease the overall length of the system or the number of lens surfaces in optical systems beyond the capabilities of aspherical and freeform surfaces. This implies that the slim profile of the flat lenses is the key factor in their potential for miniaturization. Nothing more, nothing less. Ultimately, flat lenses offer a notable and intriguing addition to the array of tools for optical design. The usefulness of flat lenses changes significantly based on the context of the application. In conclusion, we are convinced that it is crucial to integrate flat lens technology into lens design workflows to fully comprehend and utilize their capabilities. It is time to practically evaluate the potential of flat lenses and move beyond mere theoretical debates. As mentioned before, the primary challenge in integrating metalens into a multi-scale modeling framework is creating a metalens simulation model that can seamlessly interact with the simulation models of other components, such as traditional lenses. Next, we will explore the solution to this challenge. Lens systems convert wavefronts originating from object points into wavefronts that create the image points. Wavefronts are mathematically represented by their corresponding phase function psi, which we call the wavefront phase. The wavefront phase is of pivotal importance in both the design and simulation of lens systems. In general optics, the wavefront phase is directly connected to the local ray direction vector as through the equation here, where this symbol here represents the x and y components, and as that is determined by knowing its a unit vector. In physical optics, the wavefront phase retains its crucial significance. It is now integrated into the electric field vector E through the equations here. In multiscale physical optics simulations, the wavefront phase psi is utilized as a continuous and smooth phase that is shared across all components. Electric field components can possess extra phases, the argument of U, such as a vortex associated with an angular momentum beam. For instance, the phase of this Gaussian or of Gaussian-Laguerre beam, order O1, is here shown after propagation and can be broken down into a spherical wavefront phase and a phase dislocation. The separation of the wavefront phase from other phase contributions of the electric field components is one of several concepts that endows virtual fusion with its exceptional lens modeling capabilities. Let's examine the manner in which a lens alters the wavefront phase. Conventional lenses modify the wavefront phase through the optical path length between their surfaces. The phase is derived from the OPL just by multiplication with a vacuum wave number KO. This outcome is equally valid in the realm of physical optics. The resulting phase is continuous and not expressed as modulo 2 pi, meaning it is unwrapped. The variation in the wavefront phase psi is independent of the polarization of the electric field in this case, for the OPL. And from a simulation perspective, this represents a highly relaxed numerical scenario. Next, let's consider the case of a flat lens. The influence of the flat lens on the field at any location on its planar surface can be characterized by this matrix equation with the quadratic matrix M. In the subsequent discussion, the z-component of the field is irrelevant and can be calculated on demand. And thus, for the sake of simplicity, we omit this special symbol. The values of the matrix M can be obtained using any suitable simulation model of the flat lens surface. Specific decisions regarding the surface structure of the flat lens and an appropriate simulation model for M will be addressed as necessary. The subsequent analysis of the impact of a flat lens on the wavefront phase applies to any kind of flat lens and shows a simulation model for the matrix M. Thus, we shall proceed with the analysis. The wavefront phase of the incoming field can be explicitly separated from the matrix multiplication, leading to this expression, where the output wavefront phase is expressed as the input wavefront phase plus the wavefront phase response of the lens. This phase psi represents the change of the input wavefront phase due to the flat lens. In the case of flat lenses, the phase response psi is not determined by an OPL between the lens surfaces, but rather must be derived from the matrix effect on the input field represented by the matrix multiplication. Given the critical importance of the phase, of this phase psi, in the modeling on design of lenses, it is essential to develop a robust method to calculate the response psi using the matrix effect on the input field. The essential factors that define M, and consequently the wavefront phase response, include the local structure defined by the parameter vector P, here for two types of metacells, the direction of local incidence, S in, and the wavelength lambda. I would like to stress that the local direction vector is defined in the same way in physical optics as it is in geometric optics. To summarize our understanding of the dependencies of the matrix, we express the matrix as a function of the structural parameters, the local incidence direction vector, and the wavelength. In mathematical terms, the dependencies of the matrix are represented by M of P, S in, and lambda. In the realm of metalens modeling and design, possessing an in-depth understanding of the matrix values is absolutely paramount. This knowledge spans across the parameter space, the directional domain, and the wavelength range. I would like to point out that any method you might come across within the optics industry, software industry, that does not utilize the complete modeling matrix across the relevant parameter, direction, and wavelength domains is insufficiently developed to offer the necessary tools for exploring the potential of flat optics in new applications. Therefore, we compute all matrix values across the parameter space for a chosen type of metacell structure, the pertinent direction domain, and the applied wavelength range. These matrix values function as nodes within a neural network, or more traditionally, a comprehensive data network, connecting the parameter space, the directional domain, and the wavelength range. This neural network encapsulates all the modeling and design data for a metalens with a specific metacell configuration. It is important to note that this network only needs to be computed once for each type of metacell structure. If you are working with pillar type metacells, you do it one time. If you're working with nanofins, you do it one time, and so on. Employing advanced modeling methods on a typical laptop, the time required to set up the neural network varies from a few hours to several days, depending on the number of nodes involved. Virtual Fusion supports distributed computing, which allows for an almost linear decrease in computation time with the addition of more clients. In summary, the network computation is not a practical limitation in flat optics modeling and design. Going forward, we will operate under the assumption that the network is already established and prepared to furnish all necessary details regarding the matrix elements. With the network established, we now address the task of determining the wavefront phase response of a metalens. First, we must grasp the essence of the task before us. For clarity, the discussion will focus on a single wavelength. Given a particular U in, the network supplies the magnitudes of the matrix effect for both components, magnitudes, and the phases. Let's examine a few examples where we utilize two types of metacells with these specifications here and different input polarizations. In this first example, we employ linearly polarized light and determine the amplitude outcomes for both the pillar metacell and the nanofin metacell based on their respective structural parameters. Here you see the results for the phases. The nanofin structure exhibits significant differences between the X and the Y component results, unlike the pillar cell. Next, we alter the incident light from linear to circular polarization and examine the resulting amplitudes and phases. Clearly, from these results, it is typically necessary to consider the polarization effects of metacells. which raises the issue of determining which phase should be identified and treated as a wavefront phase response. The X component and the Y component are two clear options. However, what should be done if they differ? From a mathematical perspective, we must choose a suitable candidate for the wavefront phase response and extract it from the outcome of the matrix multiplication. If we do this, then we find this mathematical situation as here. We obtain the residual phase components by taking the matrix component phases x and y and extract the common phase candidate we have selected. The candidate's quality should be assessed based on the residual phase left, taking into account the magnitudes of the components. Without delving here into the detailed definition, it is sufficient to state that we use a secondary momentum criterion on the phase residuals to evaluate the quality of the candidate. The quality measure is represented by a single value denoted as sigma square. This table represents the sigma square values for the previously discussed examples, utilizing the phase of either the x or y component from the result of the matrix multiplication as the wavefront phase candidate. The sigma square values clearly demonstrate the significant polarization dependence of the nanothin structure. It is evident that in the case of linear polarization, both candidates are inadequate for nanothin metacells. And without a suitable wavefront phase candidate, or wavefront phase finally, designing the metalens is unfeasible. This outcome emphatically illustrates that the straightforward method of choosing the wavefront phase as either the x or the y component from the matrix multiplication result is inadequate for the design and modeling of metalenses in any serious software development endeavor. This simplistic approach falls short of providing a robust and reliable foundation, highlighting the necessity for more sophisticated and nuanced methods to achieve viable and effective metalens modeling and designs. Consequently, we propose a technique for the design and simulation of metalenses that fully leverages the capabilities of the established neural network. It is important to recall that the nodes in the network are represented by the matrix values, which are computed based on a selected metacell geometry and parameter space. To perform this computation, an appropriate simulation model needs to be utilized, and we need to talk about it now. Given that each meta-atom is surrounded by neighboring meta-atoms, the matrix analysis is conducted not on a single isolated meta-atom, but rather on a meta-atom that is replicated periodically. This leads to the formation of a sub-wavelength grating, where the meta-cell serves as a periodic unit for analysis. The analysis of this meta-cell grating employs the Fourier-Modal method, also known as RCWA. We call this effective technique the periodic cell approximation. Towards the end of the webinar, I will briefly discuss the advancements of the PCA method. Now, let's continue with our modeling and design procedure concerning the wavefront phase response. In the subsequent step, we train the network to identify an orthogonal vector basis W1 and W2, which yields the optimal wavefront phase candidates Psi1 and Psi2 by minimizing our merit. Upon completing the neural network training, the mode and phase candidate outcomes are embedded within the network, making it ready for application. The training of the network for our two example structures reveals the ordinal basis shown in the table. As software developers, it is crucial for us that this neural network training concept provides a fully automated technology. It allows any user to choose one or more metacell geometries and initiate the training process, which produces everything required for successful metalens modeling and design. To transmit the incident light through the metalens, the initial field is first decomposed into the modes supplied by the network, the modes we just found by the orthogonal base. The network training has already resolved the modeling for both modes, allowing us to derive the output field. Typically, this field is composed of two modes. However, when the polarization dependency is minimal, the phases may align, allowing a single mode to adequately represent the output field. The potential presence of two modes in metalens modeling is not surprising. This phenomenon is also observed in birefringent media. The polarization effects observed in nanostructured surfaces, even when fabricated in isotopic media, are also referred to as form birefringence. I intentionally omitted the candidate indication here of the phases because in the modeling process, the final transition from candidate to the ultimate wavefront phase response of the metalens is executed. The phase candidate, the selected one, is not yet in the form of a wavefront phase, since it is in the form of 2 pi modulo. In addition, it may include some contributions which do not belong to a smooth wavefront phase, for example, because they cannot be unwrapped like a phase vortex. This serves as an example here of such a situation. We have seen it before. Thus, in a final step, the phase candidate is unwrapped and filtered. We refer to this operation as theta and obtain this equation here. So we take this operation and then we get our wavefront phase per mode and another residual from the filtering process. This method relies on spine interpolation techniques that were explored by my former colleague Irfan Badar. For documentation purposes, I would like to present the equations of the resulting output field. It is given in the form of the electric field output per mode, in the form that we have here our complex amplitude and here the resulting wavefront phase in the output, consisting of the input wavefront phase and the phase response of the flat lens, where we put such an energy on to find it. This phase now is unwrapped and smooth. And this U is a quite complex term, which comes from the matrix multiplication per component on the modes, so on the vectors we have found in the neural network, and then the residuals from the first step when we applied the modes, and the residual from the unwrapping and filtering. And then we have the weight of the mode decomposition. Next, we will examine the creation of a metalens using the trained neural network as a foundation. The design is feasible for only one mode, provided that the modes have distinct wavefront phase responses. Otherwise, you can just take one because it's the same. Thus, one mode must be selected. Then we specify the requested wavefront phase response we like to see, or you like to implement. which the metalens should be designed. Alternatively, you may choose a thick lens surface within a lens system, which is to be substituted with a metalens. Virtual Fusion can determine the required wavefront phase response for you in this situation. Next, we utilize the neural network to position the meta cells with the appropriate structural parameters on the designated lens surface. Lastly, the manufacturing data, such as in GST2 format, is produced. The simulation and design techniques are incorporated into our proprietary VirtualLab Fusion software. These advanced settings are planned to be released to the public in the upcoming 2024 software updates. That means this year. Let's now delve into some truly outstanding example demonstrations. Let's enjoy the simulation power facilitated by the techniques we've just discussed. Let's start with the pillar type focusing metalens. Here you find the specifications along with the segment of the GDS2 data for the lens. By employing the neural network, the lens design is completed within 2 seconds. Approximately 7,500 times 7,500 meta cells are arranged across the lens, which has a diameter of 3 millimeters. The ray distribution within the system is obtained from the multi-scale simulation, along with the magnitudes of the field at the focal plane. In this case, for light polarized linearly along the x-axis, no crosstalk into the y component is observed. In this example, as well as in all subsequent ones, the simulation time ranges from approximately 10 seconds to less than a minute on a standard laptop. It is also possible to determine the irradiance at the focal plane. The PCA model estimates the efficiency to be around 94%. We will observe later that this estimate is somewhat overly optimistic. We will see and discuss later. Upon altering the polarization of the input field, the outcomes appears as follows. By carefully analyzing the wavefront phase response of the metalens using our neural network, we can also examine the aberrations caused by the metalens. For the off-axis plane input field, we derive this dot diagram, the field magnitudes, and the irradiance at the focal plane, here with dot diagram superimposed. Next, we substitute the pillar type metacell with the nanofin type metacell. Here we have 2 modes, so we must select one. The design is done for one of the orthogonal modes, here for the white circularly polarized field. Then we obtain these rays, and the magnitudes after lens appear like this. Due to the high frequency modulation, Moiré effect leads to this somewhat unusual appearance. A closer inspection uncovers the high frequency modulation. This arises from the ambient modulation across the parameter space, which we noted during our discussion on the neural network. The modulation causes also a slight reduction in efficiency. The field magnitudes at the focal plane and the irradiance can also be readily calculated. We now switch the circular input polarization from right to left, and the impact on the ray distribution is clearly visible. The lens exhibits a divergent behavior. The calculation of the irradiance on the same plane as before confirms that result. In the next example, we substitute an aspherical lens surface in this beam expander setup with a pillar-type metalens. VirtualLab determines the required phase response for the metalens automatically after the surface to be replaced is selected. The metalens has a diameter of about 5 mm and comprises 12,000 times 12,000 metacells, ensuring its functionality. The trained neural network completes the design in 7 seconds. The performance of the metalens is showcased by the irradiance behind the lens and the calculated vectorial point spread function. Prior to delving deeper into the simulation models, I would like to demonstrate one final example where the two modes of the nanofins are utilized to create a bifocal lens system. We begin with a spherical lens positioned after the metalens. Then the multi-scale simulation approach provides ray results which show clear spherical aberrations for both modes. This example demonstrates that our approach enables the incorporation of metalenses into optical lens systems, offering thorough access to aberration analysis. Next, we design an appropriate aspherical lens and conduct the experiment again. For the mode with wide circular polarization, the focal point is observed at the first detector location. When switched to the left circularly polarized mode, the focal point moves to the second position. When the input light is linearly polarized, both modes are produced in the output, resulting in 2 focal points. The metalens allows for the extra encoding of a phase dislocation, resulting in the irradiance dropping to 0 at the center of the focal points. The presented examples illustrate the capabilities of our cutting-edge metalens technology that we have created and integrated into VirtualLab Fusion. It will be launched to the public, to you, later this year. Let's now take a closer, more critical examination of the periodic cell approximation. In the PCA, it is assumed that the neighboring metacells are identical. Practically, each metacell is encircled by additional metacells which differ in structural parameters to varying degrees, thus interrupting the periodic cell condition to some extent. This situation particularly arises when a cycle of the lens zones is completed, causing the structural parameters to revert to their initial values. This results in discontinuities in the structure, leading to the production of additional stray light, a phenomenon also well recognized in diffractive lenses. Thus, the challenge lies in effectively integrating the neighboring metacells in a simulation model to more precisely represent the structural discontinuities. For such a model, it's crucial to account for the structural jumps. Simply including the immediate neighbors is insufficient for enhancing accuracy. We propose using a local metagrading approximation akin to the modeling of diffractive lenses. This method not only provides high computational efficiency, but also distinguishes the stray light from the desired light in additional orders. These extra orders have clearly defined wavefront phases, allowing them to propagate through the lens system together with the intended light. Here's another illustration of the local meta-grating approximation. Again, the rigorous Fourier-Modal method is employed for analyzing the local meta-gratings. The differences in results between the periodic cell approximation and the local meta-grating approximation can be systematically analyzed by generating meta-gratings with PCA and subsequently simulating them using both the rigorous Fourier-Modal method and PCA for comparison. We have carried out this procedure and obtained the following results for the pillar-type metacells. We created meta-gratings with a period that decreases, expressed here in the table as multiples of the wavelength. We also specify the maximum numerical aperture of the lens that can be designed with this period if we assume that this period is the smallest one we use. Next, we present in this table the efficiency of each grating in directing light into the intended order, contrasting the results obtained using PCA and FMM. Subsequently, in the table, we show the same analysis for the reflected light. In the final column, we present the efficiency of all higher transmitted orders as calculated using the FMM. To compare the calculated wavefront phase responses, we present results for both the PCA and FMM for comparison. We will start with the largest period. Here's a single period of the meta-grating along with all the efficiency values in the table. The results obtained from PCA closely resemble those from FMM, although FMM exhibits a marginally lower efficiency. As anticipated, a slight phase deviation occurs at the structural discontinuity, but not too much. Now, reducing the grating period further confirms, step by step, that while PCA predicts phase values well, we can see that by comparing here the phase behind the grating period, PCA compared to FMM. So PCA predicts phase values well, but it does not effectively account for stray light in high reflected and transmitted orders. When the grating period approaches the wavelength of light entering the resonance domain, PCR becomes ineffective. The response becomes also highly polarization dependent. The resonance domain, the resonance region of local gratings is unsuitable for lens design, thereby restricting the highest achievable numerical aperture of the lens for this metacell type. We summarize for the pillar type metacell. The PCA model offers high precision in phase modeling and design outside of the resonance domain of local gratings. PCA is unable to forecast the emergence of stray light in higher order reflections and transmissions, but the local meta-grating approximation can achieve this. We plan to integrate a tool into our VirtualLab Fusion software to conduct grating analysis similar to the previous example applicable to metagratings regardless of the type of metacells used. This allows you to gain a preliminary insight into the capabilities of the chosen metacell. In addition, we enhanced the neural network by incorporating the local metagrating approximation simulation model, allowing it to execute the extended modeling as well, and by that giving much better predictions of the efficiency and also small corrections of the phase values. This method, this local grating approximation method, is already implemented in Virtual Fusion for diffractive lenses, and we will make it available for metagratings also At the conclusion of the webinar, I would like to provide a quick overview of our strategy to advance the simulation model further. Integrating the PCA and LMGA simulation models into our neural network approach offers a commendable balance between accuracy and speed for simulating flat lenses within lens systems. Nevertheless, they do not completely consider the specific grid arrangement of the metacells. From a modeling standpoint, this phenomenon results in a slight increase in stray light, which can be interpreted as a consequence of the metalens' intrinsic roughness. We like to make the point that this intrinsic roughness plays a similar role in metalens modeling as modeling the roughness and other defects of traditional lens surfaces. We are developing solutions for both aspects, as the modeling challenges are closely connected. The centerpiece of the approach is an analysis of the scattering effect of the metalenses and rough surfaces. To achieve this, we have devised a free-modal method in combination with perfect mixed layer technology that utilizes lateral decomposition of the incident field alongside distributed computing. In one of our recent releases, VirtualLab Fusion has introduced distributed computing in a highly user-friendly manner, combining the results of all clients in the computer network provides a simulated result of the entire metalens. This allows for a thorough investigation of the scattering impact of lens regions, with the area size being adjustable based on the number of clients in the distributed computing network. Keep an eye out for further updates of VirtualLab Fusion on this topic. I would like to conclude the webinar by reiterating that flat lenses are a remarkable and exciting addition to the optical design toolkit, especially in the areas of imaging and illumination. Incorporating flat lens technology into lens design workflows is essential for comprehending and utilizing their full potential. During this webinar, I have outlined our approach to addressing this challenging problem. Our approach to solving this task is facilitated by the remarkable multi-scale simulation technology offered by VirtualLab Fusion. In this year's forthcoming software updates, we will be incorporating the flat lens technologies showcased in this webinar, allowing you to use them directly. That concludes my presentation for today. Thank you for your attention, and we are available to answer any questions you may have.
Thank you so much. Yes, we have time for a few questions now before we close. Everyone, if you have not already, please go ahead and type your questions and comments into the webinar chat. All right, so let's see. I'm going to jump right into these audience questions. And the first one I have here is, Are there limitations on the laptop performance to calculate this new neural network? So if I only have low RAM, will the calculations just take longer or will they fail?
Christian.
Okay, the calculation of the nodes in the neural network is typically not very RAM consuming. So if your laptop or PC is not too powerful, it would simply take longer. And as Frank also mentioned in the presentation, you can also benefit if you use more computers via distributed computing.
I like to add one thing in the PCA model. When we use a FMM to calculate the neural network, per matrix, we need one FMM calculation. And for the sub-wavelength weighting, that is a PCA model, that is not a problem at all. So that is on any laptop possible to do. You must really have a very, very old one. So like my student time, maybe 1 megabyte RAM or something like this. But that is really not the time anymore. When you go to the local meta grading approximation, then the gratings becomes a little bit more heavier. And I would say you would get a problem on a simple laptop. To doing metalens modeling and design, I would say a standard laptop, as Christian used in for the test calculations, it's fine.
Absolutely.
Thank you both.
Maybe one additional comment. As I mentioned in the talk, the calculation of the neural network. The cool thing with this is that all the information is collected. So it's mainly a question of time, how long it takes to do it. It's not a performance question of the laptop. That's one thing. And distributed computing is, of course, the game changer to do it fast. And as soon as you have it, then the modeling is done, and then you have no performance issue in this anymore. Yeah.
Thank you so much. All right, let's see. This next person asked, what is the simulation accuracy in terms of efficiency reported, and how is the accuracy benchmarked? As well as how are the different diffraction orders taken into account in the simulation?
The FMM calculations accuracy is always benchmarked as normal by increasing the number of evanescent orders to achieve convergence. So that's a normal numerical procedure. We have a rigorous physical method, but of course numerically it is not rigorous. There are some parameters to adjust. That's everybody who works with FMM or FDDT or so knows that, right? In fact, it's a rigorous technique, but it's a bit a critical thing to control the parameters. So the benchmark there is to increase stability in the result by increasing the number of evanescent orders. That's the standard for FMM. Quite robust stuff, I would say. It's not very, very critical. Now, for the metalens itself, it's a varying structure. And that's the reason why we use this PCA model. This was benchmarked, as I have shown, at the grating. At the grating, there is no approximation included with the FMM. It means when we compare how the PCA is working with the grating, which is modeled with FMM, that's a perfect benchmark. The FMM is benchmarked by evanescent orders, so it's fixed. On the other hand, the PCA is compared. So the table I have shown is a benchmarking how accurate the PCA is working. Now we apply this grating approximation in the metalens locally. That's again an approximation, that's for sure. It is very, very established in diffractive lenses with a very, very good results, I would say. And in metalenses, there comes this extra trouble from the grid, which I mentioned at the very end of the webinar. And here, the benchmark is still to be done. But from the experiments, we know it's we see there is absolutely no issue. And in particular, it's a little bit about, I would say, as I mentioned at the end, it's a question, what's the benchmark of modeling a lens if you don't include the roughness? Nobody would be stopped to do lens design because he's worrying that the roughness is not included. The roughness inclusion of a lens system is still a troubling thing. It's not easy to take a rough surface with a BSDF or something, to put it in and then to calculate the PSF. On the same level, I would see this final thing. It means that's what I said at the end. I think the predictions of PCA for the face is already very good. the so the experiments are reliable. I would completely say that by the comparisons we did. Then the inclusion of the meta-grading approximation gives a lot of information about the efficiency of the meta-grading. If you then still think that everything is great and the metalens makes a lot of sense for you, then you are at the level what the lens designer is when he has a lens system ready. Then there comes the tolerancing. And then we need to talk about fabrication tolerances, this final intrinsic roughness, and so on. Then we are on this level. So I would make the point, or would argue like this, that in the meta lens community we are a little bit stuck in don't go ahead to investigate where meta lens can do something for us, because we think we must first model the roughness of the lens. It would be almost the same as with smooth surfaces. I would like to make this argument. But the good news is, even for this last step, we are preparing a technology. That means the final benchmark is a rigorous simulation of the whole thing, of the lens, just not in the lens system, that doesn't work anymore, of the whole thing. And then we can do a benchmark there also. But this is absolutely a thing where we need distributed computing, and we would not do it every day. But you would do it if you have an application where you say everything is fine. Now I need this final test before I go into production of this meta lens, and then I think we prepare this also to do. I hope that answers the question. But I really think in the meta lens community we should a little bit more pragmatic and go ahead and try if a meta lens makes sense for us. And the PCA is already good together with the local meta-grading approximation. It really gives almost all answers you need. And if you then still think the application is cool, yes, I like this meta lens, then I would probably say then do two things. Do this roughness test. If you do it really also for real lens, probably not. You build first a prototype, right? So a little bit in this scenario, I would say.
Great. Thank you so much. And I think we'll have time for one more question. So this next one I'm going to ask is, do I have to choose the shape of my metastructure before starting the design? And how do I know which kind of geometry will be suitable?
It's a very, very good question. Definitely you need to know it, because otherwise you don't know which kind of design you can do, because you don't know the phase response, right? So, but you can of course select different structures. I would recommend definitely to take one. I would say you go to your fabrication partner and talk with the fabrication partner what kind of structure they can fabricate. And if you are not interested in polarization effects, I would urgently recommend a symmetric one. If you are not afraid of polarization effects, then with our neural network and the training to find the modes, you will find the mode, the polarization which is best for you, but then you are fixed to this polarization. I showed the example where it is funny and also interesting to use two modes, but probably not often. So I would say the freedom of the structure is not restricted in the design from our side, but I think it's mainly restricted by the fabrication partner. And I also would say, if you don't like to have polarization effects, then it is somehow restricted. So I would take a list of structures which make sense from a fabrication point of view, and also with the tolerancing. Well, you can try them, because our algorithms now is completely automated. We can try which brings the best result. So you can train the neural network. You need always, for each structure, you need to train the network. Then you have different networks, of course. They're working together as one. And then you can do the design. Sometimes people suggest that you should do different structures, such as cells, at different places in the lens. I'm not really convinced of this at all, because then you introduce even more structure jumps and discontinuities in your system. I also don't know exactly why you should do it if one cell is doing the job. So that's my opinion about it. But the design algorithm we have now developed is exactly as flexible that you can take any kind of structure and then to compare it.
Perfect. Thank you so much. And everyone, if you have not answered your question already, please look out for a reply from us later. But if you do think of another question, you can let us know by emailing webinar@photonics.com. That's WEBINAR@photonics.com. And just a final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that recording by email. So finally, I'd like to thank Frank and Christian one last time. Thank you guys for participating and presenting today. And I'd like
Pleasure.
to thank everyone in the audience. This webinar was presented by LightTrans and hosted by Photonics Media. So thank you, everybody, and have a nice day.
Bye-bye.
Bye-bye.